Monday, 8/26/02. We're going to, I'm going to give an overview of how we do our hydrogen exchange game here. This will be a preamble to then going in and look at each of the pieces of equipment and devices to again get an overview. Again, as we go through this tape, the main thing for you to do is write down things that don't make sense or that you need further clarification on, because after you've looked at the tape or reviewed it, those will be the talking points from which we'll go over things. Okay, so the general structure of what I'm going to talk about today is, first of all, go over the kind of preliminary things that are advantageous for you to know before you even embark on this stuff. And that can be broken down into having at least a little bit of knowledge of mass spectrometry. And we're going to set up a little pile of reading stuff that you can go over that certainly not a comprehensive overview of mass spec, but it at least includes most of the things you need to know. And we'll also be touching on some of that in one of these little lectures later on too. Along the same lines, reverse phase HPLC, the fundamentals of what you need to know about what that process is and how it works, and as it pertains to what we're doing. Third, exchange, background for hydrogen exchange studies, some articles that sort of give a review of the theory and practice, at least the practice before how we do things. And the bottom line is what we do is a bunch of little minor improvements to what previously had been called medium resolution hydrogen exchange, as practiced by reverse phase, HPLC, and mass spec. But the bottom line is that the final result of all those little improvements is actually a big improvement. Finally, we'll have a bunch of articles and books that you can look at if you need to strengthen your general knowledge of protein structure and function as a general exercise. So that'll be 4 sets of reading materials that we can go over. Everybody comes here with strengths in 1 or 2 things, but never in all of these. So it's always useful to review that stuff. Again, same thing, when you go over that material, the main thing is for you to flag things that don't make sense or they need further clarification on. That's an excellent way to review this stuff with us. So we'll orient you to those things. The next, if we think about the sort of the categories of what we do here, there is experimental design. How do you think about designing an experiment to accomplish whatever your goal is? There's actually preparing samples. How do you physically do that once you've decided on what a particular experiment is going to be? There's then how you take those prepared samples and put them into the device, which we'll call the DXMS device. DXMS meaning Determine Exchange Mass Spec our way. But basically how you put those into the device and then set up the device to do whatever it is that you want it to be done on it. That, in fact, is what Jack Kim spends most of his time doing, and is the hardest thing to learn. If things go well, if you wish, you can treat that as a black box. If you just simply know what it's going to do, you arrange for the correct input into that, and then analyze the stuff that comes out. I'll just briefly mention what's involved in that. There's understanding how to physically load the samples in the auto sampler and make sure it's configured properly. Then there is how to set up the sequencing hardware and software that actually runs this, it controls and executes the step of operations that take place in processing your samples. What it does is basically, come on in, Amelia. Do you have a notepad? Why don't you grab a notepad and come on in here and have a seat. But it basically runs the valves in a timed manner to put various solutions together, flow your sample over after the auto sampler has suitably prepared it, and triggers off the mass spectrometers when they're supposed to go to acquire your data. So we'll call that the DXMS machine. Whoa. The next component is the mass spectrometers can be thought of as simply a minor part of this device. And in fact, in operation, they're the easiest part of this whole thing, is actually operating the mass spectrometers. Again, that is in essence a black box for first approximation in terms of how we do our studies. We have two different mass spectrometers that probably most of the time are going to be operating in parallel on your samples. One a ion trap LCQ, and the other a time-of-flight mass spectrometer at QTOF. Both are electrospray machines. The output of that, of running it on the DXMS machine, your samples, is the acquisition of data sets. Each sample takes roughly, at present, about a half an hour to be its data to be acquired. If things go according to plan, we acquire things during the daytime that you want to sort of look at one by one, or problematic samples, and overnight we run things that you've prepared earlier in the day or sometime prior, and then run automatically overnight. But the end of all this is having a bunch of data in the computer. It's then transferred over to the computers that are actually going to be doing the processing, and then is processed by special software we've had written, which we call creatively the DXMS software. And that software does a variety of things, but the most important things they do is to help you identify each of the fragments in a digest you've prepared. Very important during the when you're trying to fragment up as well as you can the protein under study, so that you can follow hydrogen exchange behavior. And finally, once you've established what we call a digestion map that is suitable to your purposes, then you're going to be performing that digestive regime and analytical regime that generates those fragments on a bunch of deuterated samples that you functionally deuterated. And there the DXMS software is able to deal very effectively with that very large amount of LCMS data and basically find all the peptides you want to follow and figure out for each one of those how much deuterium is on them. It doesn't exactly do that. What it does, it tells you precisely what the weight of the peptide is, but you also measure the weight of the peptide without any deuterium on it. And the difference between those is, with some correction factors, is how much deuterium is on there. In fact, that step, that very last step where you actually compute how much is on each peptide, is done on a spreadsheet that Dennis Panasatos has prepared, that you input all this data into, and it dances away and does a couple of things. It quickly performs these corrections for deuterium losses that have occurred in your experiment, calculates how much deuterium is on each point. If you have a time series for a given peptide or fragment, it'll automatically plot all those out so you can see what your buildup curve looks like. And then finally, it'll print out a map. Very important when you're doing your digestion fragmentation tuning. It'll print out actually a map against sequence of what peptides you have. So that's the basic setup at present, and it's probably what I've just described to you is how things are probably going to be for the most part for the next year. Things have been rapidly evolving, and things will definitely change, but it should be sort of this kind of scheme for the next year or so with minor changes. Okay, so each of those categories of things I'm now going to go over in a little bit more detail, mainly to just give you enough of an orientation so that as you're learning each of the critical items, you'll at least have some kind of context for all of this. Let me start off by saying that we have some people here who are making hydrogen exchange, as we do it here, their life. So they're learning every part of this in great detail, and that's something that ultimately takes a couple years to do. There are other people who are using this as just one of many approaches to study their scientific questions, and for those investigators who are not interested in necessarily spending their life on this, what we suggest they do is, first of all, learn how to design the experiments, learn the background. Either they or we or somebody they train to do so, have them actually prepare the samples And then we or that person puts them in the machine and runs things, and basically something they're not involved in. And then the next step where they come in is during the analysis steps, where it's basically the last step of the whole procedure, where you're finally looking at what the output of the whole process has been, making corrections, editing, basically, and proofing what the software has done right before you reach your conclusions about what's happened in terms of things. And so for people in that category, their involvement is experimental design and then using the software. And for that reason, we found that the most bang for the buck, once people were done with all this kind of stuff, to spend your time learning how to use the software. As we'll be discussing, we have several workstations here in the lab where you can run this software, and shortly we will have it set up so that you can be anywhere in the world and run the software in our lab from any PC you've got hooked up to the internet in any manner. So you're free to do this at home, whatever. So why don't you shut that off just for a second? Good thing we didn't. Or has it been going all this time?
No.
Good. Start. Okay. So let's go over experimental design. And the thing to keep in, so what the exercise is here is that you're going to take, there's two steps basically to the overall approach. And the first one is to attach deuterium to your protein or binding pair of interest in a manner reflecting exquisite aspects of function of your protein. And that's totally up to you to decide what that is and the skill of your designing things. So this is the point at which all your prior knowledge about your protein, what it likes, what it doesn't like, in terms of buffers, how to manipulate binding interactions, manipulate structure, conformation changes, all of that stuff that you know, this is the point at which it's very important. It goes into your design. It'll determine, there is no fixed buffer for doing these in. It totally depends on what your protein likes or wouldn't like. There's no fixed cofactors or anything. You bring to this your knowledge of disulfide linkages, glycosylation, what concentrations it can tolerate when you try to concentrate it, how much you have to work with, speeds of binding interaction, of pair formation and binding interactions, affinities. All these things are critically important to optimally designing the experiments. But the bottom line is that you're going to have your protein exert its normal functionalities, except that it's in the presence of some deuterated water. So the only thing special, as part of what we do at this step, is to dump in some deuterated water. But otherwise the buffers, everything else, is exactly as should be done for showing the functionality of your protein. There's folded proteins, structured proteins in general. The rates of amide exchange can vary from up to 10 to the 8th to 10 to the 9th fold slower than what you normally see when they're in random coil and fully solvated. In some of the reading you'll be doing, you'll see the theory, but simply put, when a polypeptide chain is unwrapped and water molecules have free accessibility to an amide, basically it's an acid or base catalyzed exchange reaction. Its nature is very well understood, but so the being can be either acid or base catalyzed. There's in fact a minimum, an optimal minimum, which when you're in pure water is around a pH of 3, 2.7 to 3. When you're not in pure water, when you're in a aprotic but water miscible solvent like DMSO, acetonitrile, whatever, in general the optimum pH, the slowed pH, starts rising. So for example, in 50% water, 50% anything, dioxane, whatever, you may find the optimal pH is more like about 4, and that the rate is actually maybe 4-fold slower than it would be in water under otherwise 100% water under similar conditions. So that's in random coil. In fact, exchange of all amides is not equivalent in terms of rate. It depends on what the two side chains are of the two flanking amino acids. This has been well worked out empirically by Walter Englander. We call that the Molde-Englander equations. There's a little program where you can, called HXPEP, which you'll have access to, where you can play around with these things. Dr. Englander in a couple of papers, one first time I think about 15 or 20 years ago, and then more recently about 5 years ago, empirically measured by NMR, basically exchange rates in random coil for various amides between different combinations of amino acids. And what he discovered was, as best you can tell, all you have to do is know what the two amino acids are on either side, and you can calculate what the rate is. It doesn't matter what's even further away from those at all. And so just by knowing what the two side ones are and roughly what the pH is that you're doing things, you can calculate what these should be. And as best we can tell, there's some controversy about this, but not in our lab. As best we can tell, we think those equations are correct. We've seen no indication they're not. There's a real simplification to this equation, which is basically it was designed around the kind of amides you get between polyalanine. Polyalanine is a long history being used in amide exchange work as sort of a standard polypeptide. Poly-D-L-alanine. If you make poly-D or poly-L, it precipitates out a solution. So you make poly-D-L-alanine. And basically, the random coil, 0 degrees, poly-D-L-alanine, those amides exchange with a half-life of about an hour under those conditions at pH 7. If you switch to the minimum pH, which again I said was around 2.5 to 3, that rate goes to about an hour, half-life for exchange. So that gives you an idea. We use this as one of our tricks to facilitate localization. Operationally, you do the functional labeling under whatever pH your protein likes, pH 7, pH whatever, and then when you're done, when you want to lock everything and basically stop exchange, lock things in place, you shift to this acidic pH and cold. And that's also called establishing quench conditions. So you're quenching hydrogen exchange by shifting to pH 2.7 and cold, usually as quickly as you can. In a folded protein, these rates can, as I mentioned before, become markedly slower than that. So you have an amide that is exchanging once every month or something like that on average. And the real question is, in a well-folded protein, how do these, if something's well-folded and never comes in contact with water normally, how does it ever exchange with hydrogen and water? And the idea is that, well, there's no perfectly stable protein, that proteins are wiggling around all the time. There is localized and then more global unfolding taking place all the time, and that in fact the frequency, how often a particular amide becomes exposed to solvent water is a function of how stable the structures are in its environments, the things that do hide it from water. So in that sense, rates of exchange are in fact measures of how stably hidden from solvent water a particular amide is. And that's probably one of the major ways in which the information is treated and used. Basically, these amide hydrogen functioning as water molecule-sized probes of free energy change in a protein or polypeptide. So I had mentioned that polyalanine, those numbers, remember, 0 degrees, pH 7, half-life of about a half a second, and the same one at pH 2.7 being about an hour. If the two flanking amino acids are different than polyalanine, the number is different. And it's been, as I mentioned, empirically determined by Englander. You can see it in this equation, but they can vary by up to, I forget what it is, like 300-fold from that number. Some slower, some faster. And basically the way to think about it is that things that interfere with water getting in and making atomic contact with those amides, side chains that are going to do that are going to slow down exchange, even though it's random coil. So very bulky hydrophobic residues can slow things down, and so on. And that's what you see in that equation. I had mentioned a simplification to that that equation. I just mainly told you what some numbers are. How it works out for most amides is that we use the approximation that they're, for all amides, they're going to be about this half second of rate of exchange at pH 7 and hour, 60 or 70 minutes at pH 2.7, with one exception, and that is the amide that is at the very end terminus of your protein. We're not talking about the amino group at the end. That goes very fast under all circumstances, milliseconds. But we're talking about the very first peptide amide. It turns out because that amino group is protonated on the end, it causes rate effects on that second amide, on that first amide, that speed it up by about a factor of 20, regardless of anything. So that means even under quench conditions, that guy is going to exchange off in about a 20th of an hour. And operationally, it usually disappears before we ever see it out the other end of our analytical system. So an approximation we presently use under all cases is if you have a peptide that has 10 amino acids, and therefore, unless there's a proline, 9 amides, you're only going to be able to follow 8 of those amides in that peptide. So the way around that is to use overlapping peptides. It turns out our enzymes cleave in such a way where you almost all the time can generate overlapping peptides that can help you out. Okay, so we've talked about the first step, which is the functional labeling step. So when somebody says, well, what buffer should, when the investigator says to us, what buffer should we use for the functional labeling step, they've missed the point. They're the guys that are supposed to tell us what buffer. And just because we've mentioned something, because somebody else uses it, odds are that it's not optimal for their purposes. The only thing we do suggest is that when you're done with the functional labeling, it's important that we do switch to quench conditions. And remember, the whole point about quench is quickly getting cold and quickly getting acid. And so if you've got a lot of unnecessary buffering capacity in your functionally labeled protein, it'll cause mischief when you're trying to robustly switch to an acid pH. You'll have to either use large volumes of the pH shifting stock solutions, or be uncertain about whether you've really switched things to acid pH. Things you don't want to do. So in general, if the buffers you would like us to work with have buffering capacities of the order of 10 millimolar, 5 to 10 millimolar, occasionally 20 millimolar, that's going to be just fine. We don't care what your ionic strength is. We don't care whatever else is in there. But if you unnecessarily have, let's say, 100 millimolar tris, then that's going to cause troubles. Almost any other additive that causes no difficulty. It's very common to have DTT in samples, even proteins that you are pretty sure have no disulfide bonds in them but are intercellular proteins. Very common to prepare those in DTT. That does not interfere with what we're doing at all. Okay, so that's the functional labeling step. Just as an aside, let me mention that, remember, these amides in a folded protein can go from half-life so your functional labeling conditions, which in general are for most things going to be around neutral pH, around pH of 7. At pH of 7 and 0 degrees, these things will exchange with a half-life of a half second, as I said, but the very slowest ones in well-folded proteins can be 10 to the 9th slower than that. So how do we measure these? Well, there's a temperature coefficient to exchange and a pH coefficient to exchange. And assuming that changes in temperature and changes in pH that you do don't change the structure of the protein, which can be a big assumption, and sometimes you need to do experiments to prove that's the case, biocore studies, whatever. The rule for pH is that for every 1 pH unit that you move, you change the rate of exchange by about a factor of 10. This rule works pretty closely when you're close to the minimum, like pH 3. So if you go to pH 4, things are going to speed up by a factor of 10, rates of exchange. If you go from 3, the minimum, to 2, things are going to speed up by a factor of 10. So following that rule, going from pH 3 to physiologic pH 3, 4, 5, 6, 7, that's 10,000-fold change in rate. And as best we can tell, if you haven't changed structure, these are adhered to pretty closely. The temperature coefficient is to change about threefold. For every 10 degrees centigrade you change temperature. So that means for every 20 degrees you can change about a factor of 10. So going from ice temperature, 0 degrees, to room temperature, 22 degrees, is about a factor of 10. And going from room temperature, 22 degrees, to your temperature, 40 degrees, 37 degrees, is again about another factor of 10. So going from 0 degrees to your temperature, 37 degrees, or the temperature of a major fraction of what we study, they're either you or things that want to eat you, bacteria, whatever, then that's about a factor of 100. So by changing pH, and also let's say during the functional labeling step, many proteins don't significantly change their structure or their functional properties across at least a 2 pH unit. So let's say going from pH 6.8 to 8.8, many proteins behave absolutely the same in terms of on-off rates and binding interactions, catalytic activities, all kinds of things. If your protein is like that, then you need to take that into account when you're choosing how to set up your experiments. The bottom line is this. Ultimately, you don't know. Remember, these peptide amides are going to serve as probes for behavior for subregions of your protein. All depends on what you're trying to study. But if you plan to study something that's could be anywhere in the protein, you're going to have to survey a major fraction of all those rate classes. So you need to study things that can exchange very fast and study things that exchange very slow. And you want to do it without actually doing incubation reactions that are much longer than a few hours and that aren't much shorter than a few seconds, if you can. And the way you can help do that is by manipulating pH and temperature. So in your functional labeling step, if you wanted to measure the very fast exchanging ones, you'd want to do things in the cold, 0 degrees for your functional labeling, and as acidic as you can without perturbing your protein. And if you don't know what that is, choosing 7 is probably a good idea. To measure the fastest exchanging ones, the slowest exchanging ones, you would want to do things at 40 degrees centigrade, easy to do, and most proteins doing things at 40 degrees is more physiologic than doing them at room temperature. So 40 degrees and a pH more like about 8. That's a pretty good guess that those are going to work just fine for you with your protein, unless there's special reasons to think it wouldn't. And again, the exceptions are truly exceptional. Thermostable bugs, all kinds of things. Of course, there are going to be exceptions. So that's what you think about in terms of your design. So as a general rule, surface phenomena, let's say you're going to do a binding interaction and you want to know what becomes sequestered from solvent on a binding event, those are going to tend to be the faster exchanging guys, but for sure there are amides that are surface disposed in a space-filling model. You can see them on the surface and they're already slowed 10,000-fold from the maximal rate. And so if you want to see how much further they're slowed by a binding interaction, you better be performing the exchange reaction at a time regime appropriate for looking at those. So there's a lot of surveying work to be done to establish what range to use for each of your probes. After the functional labeling, and let me mention this, there are 2 general ways to do the functional labeling. Let's say you have a protein where you're not going to change anything. You're not interested in conformational change, binding interaction, or anything. Then what you do is you just throw your protein into deuterated water, or buffer supplemented with it. Typically it'll be somewhere between 90% deuterated water to 50% deuterated water. You throw it in there and simply incubate, and at various times take samples out and quench them. More sophisticated experiments are, let's say you want to compare that protein with the same one when it's been bound to something else. One way to do that is to run the sample I just described to you, but also take that same protein and pre-bind it to the binding partner, and that complex incubate it for the same period of time in the deuterated buffer. and at the same time you take out samples and quench those. Then what you're basically going to do, you go through all the work and you figure out how much deuterium is going on to each peptide probe, and then just compute the differences. And the differences are reflective of differences in rates of labeling under those two conditions. We term it a protection factor. Protection factor is the ratio of rates of exchange from one state to another, as you define it. It can be a conformational change, it can be a protein-protein binding interaction, who knows what. So protection factors, and they can be protection factors you ascribe to a whole protein, to a peptidic region, or to individual amides, depending on the level of resolution you're achieving in your study. Thirdly, the most elegant way to do these functional labeling steps is if there is a change in state that you're interested in studying, you on exchange, in other words, incubate and deuterated buffer the entity in one state, then transform the state, throw in the binding partner, induce the conformational change the temperature, let's say for a temperature sensitive mutant to some protein, allow aggregation to take place if it's a prion thing, and then you, after that event is done, or substantially done, you then transfer now the complex or the altered protein into buffers that are still under native conditions but without deuterated water. And now you incubate again. So as you incubate, things that did not change their rates are going to come off at the same rate they went on. And if you do that long enough, what will be preserved there is stuff that deuterium that's in locations where they've slowed way down. This is the kind of functional labeling that Dr. Englander has used the longest and the most elegantly to study conformational changes in hemoglobin. It results in the fewest number of samples you need to analyze, better signal to noise, but it's a little more complicated in terms of its interpretation and how you actually do the manipulations. So at present, most of the people doing work here in our lab simply do build-up curves, on-exchange curves, with no off-exchange. And when they want to compare things in two states, they simply do parallel build-up curves in the two different states and compute the difference. And probably for the things you're doing, that'll be the easiest experience to do. So that's functional labeling. And then at the critical point, as you're sampling things, you initiate the quench. And as we said, it's nothing more elegant than shifting the pH and dropping the temperature to 0 degrees. As we'll discuss later on, it's critical to the whole thing that we add in just the right amounts of denaturants, other kinds of things, reductants, whatever, to allow you to do effective proteolysis of your protein. Once you've worked out whatever those are going to be optimally for your protein, we actually at present add those in at the same time we establish quench. So instead of quenching and then thawing the sample later, adding your denaturants and then proceeding, we make it so we add the quench, the reductant, whatever, all at the same instant that we execute the quench. Once you have quenched your sample, it is still liquid, and you now have a branching point. And what you could do is take that sample, immediately put it into our machine, and within the next minute have it injected into the system, shot onto the pepsin column, fragmented, shot onto the reverse phase HPLC column, loaded on there, all the fragments are looted off going into mass spectrometer. We call that liquid operation. In other words, the sample is never frozen. That requires you to prepare each sample right before it's run, and so you're trying to do two complicated things at once. You're trying to wrangle your sample prep, which for you guys would be an anxiety-causing thing. It always is when you're sitting there with your precious protein. You know, you got the machine all warmed up, ready for you. Everybody's staring at you, hoping you don't goof it up. And then all of a sudden you have to run over to the machine, this big confusing machine, and you put your sample in. So it's a real anxiety-causing situation until you practice it a little bit. That's liquid operation. When you can, it's nice to dissociate those two. For most of the people doing things, what you can do after you've quenched the sample is you can then freeze it. And there's nothing special about freezing in terms of hydrogen exchange. As best we can tell, just freezing into crystal lattice water doesn't slow down exchange of your protein. at the atomic level it's still exchanging just fine. What you have to do is really lower the temperature. So don't ever make the mistake of thinking just because your protein is obviously frozen like a rock and it feels cold, that it is necessarily cold enough to keep from losing some of the deuterium through back exchange. After you have done quench, after you've initiated that, there is no advantage to losing deuterium or having it fall off. Everything that's falling off is basically signal you're losing, and you want to minimize that. So this is called back exchange. You could call it off exchange. It's under quench conditions. In almost all cases, it's undesirable. So we call this undesirable back exchange, whatever. And that occurs at every step of the subsequent procedure. So the minute you've done quench, some's starting to fall off. Even if you freeze it really cold, and by really cold we mean at least minus 80 degrees centigrade, dry ice temperature. So you at least want to have your samples frozen to that temperature if you want to walk away from your experiment for a while. But stuff's still being lost there. As best we can tell, the way to figure out the rate it's being lost, again, follows this rule of for every 20 degrees centigrade it drops by a factor of 10. So going from 0 degrees, ice or liquid, to minus 80 is 20, 20, 20, 20, 10,000 fold. So instead of it being a half-life exchange of an hour, it's now 10,000 hours. But that's not zero. And we have very high precision in these measurements. And so I predict that if you quenched the sample and kept it in the Revco for a week or so and analyzed it as opposed to running it right away, you'd detect a difference. So you freeze things cold. Once they're frozen, you can store them, you can ship them cross country on dry ice, whatever. You want to think ahead about how you're going to transfer those out of there. It's no good to take it out of the dry ice, let it warm up to minus 40 degrees, minus 20 degrees, and then put it in the Revco. You've got to make sure that when you're transferring your samples, for sure things are staying at minus 80 in all your manipulations. And you do that by pre-chilling the recipient containers, doing the transfer down in the bottom of something that's got a lot of dry ice around it, like the dry ice storage areas. We'll show you those various manipulations. Now, it has turned out, one of the tricks we have is how to melt these samples really rapidly that you've frozen away. Melt them really rapidly, but keeping them cold. So we melt pretty much at 0 degrees, but doing that very rapidly with small volumes and then automatically having them injected into our system. And what we use is a highly modified auto sampler that has a robotic arm that picks up the guys at the right time, puts the thing in a vortexer heater, pumps heat into it and vortex it, driven by some nitrogen gas, so it buzzes basically. You hear this big noise when you're in there. The problem is that for some proteins, during that intensive frothing and buzzing that goes on, they are allowed to interact so efficiently with the surface of the glass vial that we use that the protein all binds to the glass vial. And so by the time you get done with the melting, there's none of the protein left in the solution. This happens it's happened mainly with one of the proteins that we've worked with, but it's a major protein we use in a variety of forms, protein kinase A. And so it's the regulatory subunits of protein kinase A love to do this. We've tried a few reasonable things to get over it, and there's no simple solution to it. Siliconizing, plastic vials, whatever. So when that happens, you have two options. You can either choose to do liquid operation as I've described it, so now you're going to sit here and prepare your sample fresh and shoot it on, or what you can do is you can prepare your samples manually and freeze them all away, but when it comes time to run them, you have to thaw them out manually. And it's easy. It's a little less controlled than the auto sampler does it, but by taking the samples out of the dry ice, putting them in wet ice, water ice, with your hands, you can thaw the things in around the same time, but much less frothing and mixing. And then you just take the sample manually and put it in the auto sampler, and it injects it like that. And that's a lot easier than trying to prepare them and then run them, as you will see. And it's just the luck of the draw, what's going to happen with your protein. So one of the early things we do is we take some of your protein and we simply freeze it, then melt it and see what happens, see where it goes. And most people's proteins make it. for your work, it makes a big difference. So you want it to be able to do that, because otherwise you get to sit here and prepare samples all the time, right before you run them. So that's the importance of frozen operation. So we've talked about some of the overview, the important aspects of functional deuteration, then quenching, then running the samples. A few little minor things to mention at this point. Anybody have any questions at this point? What we've talked about now? How much you need. So at present we're not working at micro levels. We're working at very greedy levels. Everybody that's come to us has had tons of their proteins. In general, a good quantity to use per analytical point is 10 micrograms of your protein. It doesn't scale linearly with molecular weight of your protein and other stuff for a variety of reasons. So around 10 micrograms is a good quantity. With everything we tested so far, we get better and better results all the way up to 50 or 60 micrograms per point. Though depending on the protein, we can get good results down to 5 micrograms per point. Below that, everything disappears abruptly, probably just sticking to the sides of tubes and other things. But it all depends on your particular protein. In general, there's a premium on having your proteins concentrated when you first start. The reason being is that the usual way you add the deuterated water to the thing is simply by diluting your protein. And if you want to run 10 micrograms per point, and the sample volumes added after you've added quench and all the other stuff, the usual size of the sample size is around 50 microliters. We can do a double injection and basically just scale up by a factor of 2, so 100 microliters. But basically, you want to arrange it so that you can get 10 to 50 micrograms of your protein into that final 50 microliter or 100 microliter guy. And the killer is that at the very beginning, when you initiate your ion exchange, you're going to be diluting your thing into deuterated water. So if you're going to do a 90% deuterated water, that means you dilute your thing 1 to 10 right to start with. So things that start off at a milligram per mil concentration are just pushing the limits of being able to be done at that concentration. An easy way around that is that as we've gotten more experience with things, our precision is so good that we've worked down to where you maybe dilute 1 in 4. So you have 1 part of your protein solution diluted into 3 parts of the deuterated water buffer, and that gives just wonderful results, no problem. And probably we can go even lower than that. So that allows you to input more protein into a given volume of thing if your concentration is less. In general, most proteins don't like to be too concentrated. They don't like to be too dilute either. Your protein's going to do well if you can get it at a protein in the range of, let's say, 3 milligrams per mil. It'll do spectacular if you can get it at 5 or 6 milligrams per mil. We're going to have to do something special if it's 1 milligram per mil or less. Let's say 0.1 milligrams per mil. And the special things are of two parts, 2 kinds. One is that we have an online rapid dialysis system where basically your sample can be fed in at it's a little tube about this long. Your sample can be fed in at one end, and in roughly about 10 seconds it comes out the other end. We're feeding it in at like 5 microliters a minute. It's very slow flows, but it goes out this column at the other end in 100% deuterated water, or whatever percent you wish, without any dilution. So it's basically there's a bore dialysis tubing going this way and a sheath of deuterated water flow going the other direction where it does the buffer exchange without diluting. So if you have a protein that's starting off at 0.1 milligrams per mil, you can end up having it in your deuterated solvent still at that same concentration. So that's one way around this problem. Another way around is to just go to more sensitive mass spectrometry, so that you still prepare a sample in the same amount, but you've got, let's say, 10 micrograms or 1 microgram of protein in there, and we just do what's called nanospray mass spec, and that protein enough of it shows up to do everything we wish. By going to nanospray, basically you need 1/10 to 1/100th the amount of protein you do with what we're doing now. We have not set that up yet. We're all set to set it up. We got all the equipment. We know how to do it. have had no need yet to do that. So I think the proteins we're talking about here, the prion proteins and the acetylcholinesterase concentration is not a problem so far. All right. So we talked about amount, sample size, number of points. Okay, go to the second part. So we talked about it's a functional deuteration step, then the quench, and then you quench, and then you do the analysis. And the analysis part of the thing, basically, that whole exercise is to fragment these peptides under conditions where you don't lose too much of the deuterium from each peptide, weigh each of the peptides, and then acquire additional information and do calculations that let you back calculate how much deuterium was on each of those peptides as they were in the intact protein right at the instant of quench. So you'll get lost as you're going through these calculations if you don't keep in mind the whole reason you're doing all this is to calculate back to what it was right when you put that quench in. That's what you're trying to figure out. So we'll be going into more detail on this, but basically what's done is your quench sample has added to it denaturants, reductants, various things that partially unwrap the thing. Remember, quench always includes putting things at 0 degrees, and so you add various things that unwrap the protein partially, and it's then shot over a digestive column. Usually pepsin is the main enzyme we use. Pepsin loves to chew under these acid conditions. It's a very dense support material on the column. It's a very tiny column. It's like 50 microliter column, total bed volume. The sample is shot over it pretty fast. Average digestion times that we use are of the order of 20 seconds to a minute. Usually 20 seconds is more than enough. We've got additional proteases that cleave differently than pepsin does, but still like to do these acid conditions and work pretty quick. So we use these columns in various combinations, usually all set up there in tandem or singly. At least so far, pepsin is usually the first column that is used, though there's no special reason for doing that. No rigid reason to use. There's little technical reasons why it's advantageous, but you can imagine other experiments where you have it in any order. So, to recapitulate, your sample is vortexed in this heater mixer at 0 degrees, and the instant it's fully melted, the autosampler sucks it out of there into a loop, a stainless steel loop that's at 0 degrees, and shot online. By online, what we mean there is there's a stream of fluid flowing that's a pH 2.7, flowing over the pepsin column, then over a reverse phase column, and then onto waste. Your sample is now flipped into that flowing stream and flows over the pepsin column, so you can arrange for modulating how long it's digested by the flow rate over the pepsin column. That's the first way we do it. Or changing the size of the pepsin column. If you want something digested a lot longer, use a bigger column. We flow it over that, and after it leaves that pepsin column, it then flows onto a reverse phase support. There are two ways of doing that. At present, what we do is we just have a reverse phase column that this stream of fragments is jammed onto. As you'll learn later in reverse phase chromatography, in terms of peptides, a pretty good simplification is to imagine this is a support material, very high surface area, with a very greasy surface. And in pure water, like whatever buffers we normally use as what we call the solvent A, the first buffer, which are usually 100% water, under those conditions, every protein, every peptide will stick to this greasy support. Even though many peptides are not very hydrophobic, they're always hydrophobic enough to stick to this support. And in general, they stick to the very first part of it they see, so they all stick at the very top of this long little column of support material. So a simple way to think about it is they all load onto a disc, all the fragments at the top. Then, once they're all loaded there, and we do this usually in a minute to 3 minutes. So flow rate of, let's say, 300 microliters a minute over the pepsin column, over the reverse phase column, off to waste. Your fragments are all generated in the pepsin column. All these things get loaded and basically concentrated on the top of that reverse phase column. Remember, your sample size is 50 to 100 microliters, so at 300 microliters a minute, it's more than enough loaded onto that support material. Then, once that's loaded, automatic valve switching takes place where some special pumps come online that are going at a much lower flow rate. They're going more like about 50 microliters a minute and executing a very delicate, very precise gradient elution of this reverse phase support. And now the effluent from the column is shot into the mass spectrometer. And so we do an acetonitrile gradient. So as time proceeds, it'll start to use 0 or 5% acetonitrile and proceed up to, let's say, 50% acetonitrile, typically over about a 30-minute period. Back when most other people, and back when we first were doing this, we thought it was important to do very short gradients, short gradient elution times, to avoid losing deuterium. Turns out it's not very important at all. One of the tricks is that as you add in the acetonitrile, it's one of these solvents that doesn't exchange itself. So it's basically diluting out the water. And as you're eluting, the mole fraction of water that can exchange with your peptide that's still hung up there is dropping. So we get just about the same exchange we get with a gradient in 30 minutes as we get in 5 minutes. And you certainly get much better separations. So we'll elute off with a gradient that typically will go over 30 minutes. And the way to think about this reverse phase support is that your peptides, each of the different ones, is going to stay at that top on that disk until an exact number is hit. And when that number is hit, its percent that it wants to let go, it all lets go, that one peptide. And it all then moves at the same rate that the bulk solvent flow is coming and exits the column. That's a very, very useful way to think about this. It's different with small molecules and other kinds of things. But for peptides, that's how they behave. So there'll be an elution percent. In general, it doesn't absolutely all let go instantly. But operationally, it takes about 30 seconds. So when you do chromatography for the peptide to all let go. When you're doing really precise chromatography, it'll all let go in 20 seconds, a given peptide. When you're doing it really crappy, it'll all let go over a minute's time. So somewhere around 30 seconds is the typical peak width of any peptide that's eluted off. And it's important in thinking about design of the fragmentation things to keep that in mind. And this is pretty much invariant of what volume of, what the flow rate is of the buffers and what the gradient steepnesses are, and that kind of stuff. So this 30-second elution width is an important number. Then as each of those are coming off and leaving the HPLC column, they're then shot into the mass spectrometer, and you'll read some more about that, but basically there's a stream of liquid coming out there that is a mixture of water and acetonitrile. It's charged to somewhere in the range of 3 to 5,000 volts. It's sprayed, atomized with a stream of hot nitrogen gas, very hot nitrogen gas, 200 degrees centigrade. That all evaporates, all the solvent. Then there's a tiny little hole in the mass spectrometer. It's basically a big vacuum in there with a lot of weird electronics and metal and stuff and various electrical fields. And there's a little leak, a little hole in the whole mass spectrometer. And through that hole goes some of the sample, tiny fraction of it, thousandth, millionth, who knows how much, of this stuff you're spraying. That little stuff that leaks in there is what you're going to study. And inside the mass spectrometer, those ions now with no liquid around are steered around and various things done with them. We'll talk later about the mass spec. At the end of that, they basically are segregated by size in such a way where against a calibrated system, you get to weigh exactly how heavy your peptide is. In addition, in these mass spectrometers, we can further do fragmentation, not for purposes of localizing the deuterium, but for helping determine what the peptide's identity is in the first place. So we do use collision-induced association a lot, but for naming the peptides, not for weighing them with deuterium on them. So we'll call this the analysis fragmentation step, what I've just described right now. So you have the functional labeling step, the incident quench, and then the fragmentation analysis step. And the fragmentation analysis starts with that auto sampler melting your sample, and ends with that run's data finally all being acquired and repositioning for the next run. Typically takes about 30 minutes, maybe 45 minutes to reset to initial conditions. And operationally, what happens during that time is what we spend in terms of data acquisition and thinking about things, 95% of our time. So 95% of the hard stuff, the stuff Jack spends his time doing, and where Jack and I will be fussing, trying to fix something, whatever, on the machine, is concerned with those various steps. Those are the things that to you guys can be black boxes, unless you wish them to be otherwise. You'll do great experiments, you'll get famous if you designed your experiments well, get lots of papers out and everything, without knowing anything about details beyond what I've just said now. What we'd suggest you do is, as I said before, focus on experimental design, actually composing the samples, and then the final stage of data analysis. And once you've got that down really smooth, move into learning more about some of these other things. All right, that way you can have a lot of productivity, and we would invite you to learn whatever you wish to learn about all this stuff. Okay, so we've talked about functional labeling, quench, and then fragmentation analysis. Remember, fragmentation analysis is performed entirely under quench conditions if we've done it right. So everything's in the cold, everything's at this acidic pH. With minor deviations, that's what we try to achieve. We'll talk later on about something that should have occurred to you already. How can we, I said that nitrogen gases that we atomize it in is at 200 degrees centigrade. We evaporate the stuff by throwing it into boiling nitrogen, superheated nitrogen. How do we keep all the deuterium from blowing off if the purpose of that is to volatilize it? Right? How can that be done? So there's a lot of questions that we'll go through later on. Okay, so that a person can never come near our lab and, thinking properly about it, can design his experiments really well. He can actually figure out exactly what he wants to do. But to actually start doing the things, you have to know, before you can actually run them on the machine and get useful results out in terms of where your deuterium is and whatever, you have to establish your fragmentation pattern. What manner of fragmentation is going to optimally produce the fragment probes for your particular study. And so therefore, the fragmentation analysis step itself actually has two general steps itself, the way in which you use it. And the first is you take fragments of your protein undeuteriated. So deuterated water definitely doesn't come near anything. And what you're going to do is pretend as if there's deuterated water there, and making sure that everything is under quench conditions, go ahead and manipulate a whole bunch of things and seeing how well the fragmentation goes. The reason you don't want to deuterate those is that the assay we use for figuring out what the fragments are would be screwed up if there was any deuterium on them. So data-dependent MS2 with deconvolution programs. So the rules you have to do, you'll get into serious trouble if you say, well, there's not really any deuterated water here, so we can make these shortcuts. We can do these things. Because every time we've done that, we've usually taken another year to discover that shortcut was misleading, because it really is different if it's really under quench conditions and the conditions you got to do the experiment. So let me give you, you'll learn more later on about these fragmentation conditions, but I'll try to give you some generalizations now. We've discovered that there are several parameters that operate as independent variables in this fragmentation. And the best hypothesis that explains this is that the proteases we use basically will clip everywhere they're given an opportunity. And the opportunity means for it to be unwrapped and exposed in solution to them. But that in fact that's not a very rapid process at 0 degrees for many proteins. Far less efficient than you would think. So what turned out to be a problem, we've got to operate, do proteolysis under quench conditions, 0 degrees, this weird pH, in fact is a major bonus, because by taking very careful control of the extent of denaturation of a protein and actually making it polymorphic, having varied states of denaturation in an individual sample, now we can get the proteases to clip all over the place and produce all kinds of massive, complicated fragmentation patterns. And so long as you know how to identify all those guys and deal with it, it's glorious, because you've got all these different fragments. So these things behave, as best we can tell, pretty much as independent variables. So the type of denaturant you use, the minimal denaturant is just shifting to acid pH. So just moving something to pH 2.7 in the cold. For many proteins, that denatures them enough so that pepsin can chew on them. We've never found that to produce as nice a digest as adding in some additional denaturants. What was that?
That's fine.
Still filming?
Oh yeah.
Okay. All right. That's you? Okay. So, a lot of the literature that you'll see, they never consider any additional denaturants. It's all just shifting to acid pH and adding in some liquid phase pepsin. So we found it makes a big difference. And so the type of denaturant is important. So whether it be just acidic buffer, we typically will use formic acid, 0.1 to 0.05 is a common concentration, 0.1% formic acid to a common concentration. We also use trifluoroacetic acid, 0.1, 0.05%. The exact concentration, different ones are optimal depending on what stage of the technique we're using them in. We've spent lots of time working out exactly which helps the enzymes work precisely the best and which is the best for slowing back exchange. It actually varies. The pH rules I gave you, in fact, are not exact. There's a convention in this whole art, which is that every time you measure a pH, it's always as measured at room temperature. With and what you're reading is the readings on something that is operating in mostly a non-deuterated buffer. You then, of course, if it's going to be a quench solution, it's at 0 degrees, whatever. But you don't remeasure the pH at 0 degrees. pH electrodes are not accurate, reliably accurate enough. Well, it turns out probably chemical activity as a function of temperature varies depending on the chemical that's the buffer. And in the old literature, phosphate buffer was the main one used. And it turns out it has a very dramatic change in chemical activity with temperature, whereas some of these other things like formic acid is a lot less. So when you see discrepancies between the literature and the pHs we use, that's probably the explanation. What we do is we empirically tune it. So we spent a lot of time saying we want to use formic acid because it's volatile, for example. It's really great for mass spec. What is the optimal concentration for slowed exchange? And we just figure out what it is. What is the optimal concentration when it's in acetonitrile? It'd be different. We determine what it is, and so on. So the recipes we use have all been empirically tuned to be pretty close to the optimal. So there's that minimal denaturant, all the way up to adding in either guanidinium thiocyanate, guanidinium hydrochloride. Those are the only two we've used. We've had experience with lots of other denaturants, but we find we can do everything we need to do with those two. For most studies, almost all studies, guanidinium hydrochloride is all the additional denaturants you need, and not guanidinium thiocyanate. We will later go into the kind of tricks we use for really difficult to denature proteins of using guanidinium thiocyanate, but for the present, let me just say that it's a little more complicated than manipulations with thiocyanate. We have not found a protein yet that will not render susceptible to pepsin. The problem is that it's a careful balance between denaturation and aggregation that has to be tuned to each protein, and it can be a pain. When guanidinium hydrochloride is used as the tuning denaturant, we rarely have any problems. We've never had any problems yet with aggregation, other kinds of things. So, varying the type of denaturant, and often will vary from no guanidinium hydrochloride all the way up to 4 molar guanidinium hydrochloride at the instant of quench. A second variable is, so that's the type. Concentration is an independent variable. Then there's the time that you denature. In other words, we will get a different, depending on, for some proteins, you get a very different fragmentation pattern if you make it to 1 molar guanidinium hydrochloride and hold it there for 10 seconds and then put it on pepsin, as opposed to holding it at that concentration for 2 minutes and then putting it on pepsin. Again, this is all at 0 degrees, and the 0 degrees makes all the difference in the world. And by 0, we mean really 0. By our definition of 0 degrees is on melting ice. So it's no good if you've got a very sloshy ice bucket that's got lots of water and a little bit of ice. It's no good if you've got ice and no water. It has to be melting ice. That's the only ice that's really right at 0 degrees. So the time of denaturation, the longest we've ever done things is maybe 5 minutes of incubation. Then there's the time that it's the duration of fragmentation. As I mentioned before, it's basically how long it's in contact with the support. The pepsin, we make all of our own support materials. These are basically particles that are about 20 microns in diameter with little channels through the particles. These are rigid particles. We pack them into little columns, really jam fluid through them so that maybe 20% of the fluid goes through the tiny channels within each of the particles. The rest flows around them. Pepsin is conjugated, for example, to these at 30 milligrams per mil of support material, so it's a very high concentration of pepsin. In part, that's part of the reason why this goes so fast. The other part is the denaturants. Surprisingly, these denaturants really speed up pepsin fragmentation. It's probably the major reason why we do things so much faster than anybody else, is that we use these denaturants in this manner. And again, as I mentioned before, typically digestion times will be for a given bolus shot of the protein will be between 20 or 30 seconds and a minute, varying that by either flow rate over a small column or making the column bigger. Again, you don't want to take too much time because stuff is still coming off. So if you decided you want to do a 5-minute fragmentation for some reason, then ideally the smartest way to do it would be to make a suitable sized column where you could roar the sample onto the column, stop flow, let it just sit there on the column for 5 minutes, and then resume very fast flow to shoot it off. Presently what we do is we take of the order of a minute or 3 minutes to collect fragments from things where each little shot is only being digested for 20 seconds if you compute how long it spends on the column. They can't be digested once they've left the column. That's just easy to do. But if you wanted to digest a lot longer, it'd be silly to flow through at a super slow flow rate through a tiny column. Now to get a 5-minute digestion, you'd have to flow it at 1 mil an hour or something ridiculous. So we've got a range of different size columns to use for all these. But it has been rare, it's been never, that we've gone, actually in the last year and a half, that we've gone to a larger size column than this 50 microliter column. You can go to smaller columns if you want to. Again, we've just not had a need to do that for the studies we've done. So there's the time of digestion. Then there's the enzyme you use. There are 3 endoproteinases we use. One is pepsin, porcine pepsin, easy to come by, easy to conjugate. There are 2 others. One is called, these are fungal proteases. One is called nulase, I don't know what its EC number is, and another fungal protease 13 from Aspergillus. And both of these have all the nice attributes of pepsin. They like to trim at, as best we can tell, the full range of acid pHs we like to use. So between 2.5 and 3, they work really fine. In general, they have a more stricter requirement for good denaturation for their chewing. So pepsin, for example, can chew hemoglobin or cytochrome C up very nicely with no denaturant, no guanine hydrochloride. Though they do better. You get 2 or 3 times the number of fragments if you do add it in. Whereas fungal 13 and nulase will not chew very effectively those 2 proteins if you don't have some guanine hydrochloride in. However, if you, let's say, put a pepsin column and then a nulase column right after that, so 20 seconds is 20 seconds on the pepsin, 20 seconds on the nulase column, now you find you don't need denaturant to get the nulase to subchew the pepsin guys very nicely. The few bites that pepsin does is enough to produce the denaturation for the next guys. And there's some times when you don't want to have a lot of denaturant around. Increasing denaturant above 1 molar always slows down these enzymes. By definition, they were selected for being able to proceed with lots of denaturant around, but it always goes better when there's less. So you don't use denaturant if you don't have to. You're just going to get things going faster and more fragments. So 3 endoproteinases and 1 exoproteinases, carboxypeptidase P, which under all these same conditions basically choose from the C-terminus anything that's already been generated. So using it right after any of these, or a combination of these endoproteinases, is a way of generating little ladders of fragments. These columns, almost all the use we have of them now is they're in front of the HPLC column. We also can use these, but think about what's happening. Let's say you can make every possible byte that you can. Well, you've just got a tremendously complex digest. And so when you do your reverse phase HPLC, there's billions of overlapping peaks coming off. When you do the mass spec, there's a lot of overlapping peaks, and none of them in necessarily very high yield. So way too complicated to digest. That's necessarily going to happen if you're doing all your digestion in front of the reverse phase column. Another way to do things is to, let's say, just digest with pepsin in front of the reverse phase column, but arrange it so that as they're coming off sort of one by one, you have another digestive column sitting at the end of the reverse phase column. And so long as you can arrange it so that that enzyme works with acetonitrile there, and during the time it transits, right before it goes in the mass spectrometer, you have another way of doing further fragmentation. And we know how to do that with certain combinations of these. The trick is getting rid of the acetonitrile, and different ones of the proteins have different requirements for getting rid of the acetonitrile. And you have to be able to get rid of the acetonitrile very quickly online. We know how to do those things. We've not had a need for doing any of that. As you go to bigger and bigger proteins, so think about how this works. We said the proteases are pretty nonspecific. In general, the size of fragment you're going to want to be using is roughly around a 10 mer fragment. If you were to think of an average size, you don't want a 50 mer, you don't want a 2 mer fragment. You want things roughly around 10 plus or minus 5 for the size of your fragments. Well, if it's pretty much sequence nonspecific, then the number of fragments you're going to get from any protein is basically a direct function of how long the polypeptide chain is. Keep in mind repeating subunits. So for your thyroredoxin, transthyretin, it's a tetramer of identical subunits, 13,000 Daltons for each, something like that. So its complexity is that of a 13,000 Dalton protein. Small. It's not 4 times that. Hemoglobin, 16 kilodaltons for alpha, 16 for beta, 2 alphas, 2 betas per tetramer. So it's the complexity of a 32, right? Your acetylcholinesterase is all unique sequence, so it's going to be the whole length of that, which is what, 75 kilodaltons, 80, something like that. Okay, so think about it. What did I tell you before? I said that average thing is going to come off in 30 seconds, average peak, right? And so from something that's got 100 amino acids, let's say you're going to generate X fragments from that overlapping things. Something 5 times that size, you're going to generate 5X fragments, unique fragments. But if you run the same gradient, they're all going to come off at the same time, in the same rate. So that means with simple sequences, small, simple sequences, you can approach a situation where in any time regime, in any 30-second period, maybe 2 to 3 peptides are coming off during that time. With big proteins, during that same time, maybe 10 peptides coming off at the same time. In overlapping peaks, dead, whatever. And that's the basic exercise. So what we'll see is with the small protein, there are two, you'll learn some of this terminology of mass spectrometry, but for LCMS, one way to back up, once you've done a run to get a rough idea what's happened, has the chromatography worked. Remember, very often, it's like driving, good analogies to driving a car here. So you can win races, you can win lots of races, be a famous race driver, and not know how to tune the engine, okay? So that's an example of the black box part of the thing. So if you can figure out where you want to go, and you know how to do this, and you know when you're there, you can be a great race car driver. Also, you got to make sure when you're evaluating how things are going, make sure you're looking at the right things. So let's say if you drive to San Francisco, you're going to consume 2/3 of your tank of gas. Okay? And so you get in the car, you drive, and 2/3 of the tank of gas is gone. Good, you're finished. And you're still sitting in San Diego because you had a flat tire or something. Very often we'll acquire a set of samples. Oh yeah, good acquisition, everything. Nobody's looked to bother to see if the chromatography worked. It didn't. Yeah, you ran all the samples and you're still in San Diego. So one way to quickly, without spending all the time running through all the software, you want to back up and look to see if basically the chromatography worked. The bottom line is that you should know what it already looks like. You've already got your digestion map and you know how to get that. You know what that chromatography looks like. Look to see if a big sample set you've acquired, if it's what we call total ion current. Basically at each time point it sums up all the ions that were generated. So you see just a curve, almost like a spectrophotometer reading of what's coming out versus time. Various hoops and valleys, each one corresponding to sets of fragments. If that looks the same for every one of the samples that you ran and looks the same as your reference one, you probably, and the right amount of signal, and they're all sort of producing the same pattern, it worked. With functional deuteration, you don't change what this selected ion, the total ion current looks like. One of the predicates of this whole thing, one of the assumptions is that the method of fragmentation, the behavior to the enzymes, the behavior on the reverse phase columns, the behavior in the electrospray don't depend on whether there's deuterium there or not. They're invariant. So when you work it all out with an undeuteurated sample, it's going to be the same with the deuterated ones. So you expect the total ion current to look the same with your whole sample set you've acquired. If 4 of them is flatline, don't bother sitting down and crunching the data on that. People do it all the time. They say, we can't understand the results. You back up. Yeah, your gas tank's empty, but you're still in San Diego. You didn't bother to look. And you've wasted 3 days poring over the results, not realizing you got no signal. So don't get so involved in things that you don't back up and look. Okay, so those are the various steps. So again, I've talked about those independent parameters for fragmentation. So how it works out is, investigator comes, wants to start working with something. So let's say your prion protein, let's say PRP. The first order of business is to establish your fragmentation map. And unless we think there's special problems, what we do is we take their protein, pretend like we're diluting it into deuterated water. So we'll dilute it into PBS, whatever buffer they think they're going to use, add our quench solutions with a sort of standard varying concentration of guanine hydrochloride in it, freeze all those, and run them. We'll not freeze one of them, run it first, see what signal we get, fragments, and then run the frozen set, and if every one of them are flatline, well, too bad, it's not going to work for frozen operation for you. We'll take the remaining ones out, manually melt them, see what they get. So basically, we first start off by ranging through. What we found is the denature, so starting with the assumption that guanine hydrochloride is going to do it, but varying the concentration. And the concentration will go from none up to a final concentration of 4 molar. Using no pre-incubation, no added pre-incubation. The way the autosampler works, there's always usually about a minute's pre-incubation, even if you do nothing. During the frozen melting, there's probably an additional 2 to 3 minutes. So what we're talking about is purposely doing something in addition to that, incubating for 5 minutes, whatever. So usually we will set up a sample set where your protein is set up like I've just described. So the compartments we use for these sort of standard things are, we take some of your protein, whatever volume of it makes 10 micrograms worth. We'll dilute that down to 20 microliters under quench conditions, and then add in our quench solution, 30 microliters of a quench solution. So 0.1% formic acid, or 0.5% formic acid containing the right amount of guanine hydrochloride to hit a final target of 50 millimolar, 0.5 molar, 2 molar, 4 molar. Those are sort of the standard concentrations we use. So several orders of, order of magnitude between each. Freeze all those away, run those samples. The second thing so far that we've found that produces the biggest difference is how long you digest. So when we're doing this kind of survey, we may, over the 50, or it's actually a 60 microliter pepsin column, we'll flow the things at 250 microliters a minute, which gives them a digestion time of 30 seconds, something like that. or float at 100 microliters a minute, which gives it a digestion time of 2.5 times that. And then just elute it with a 30-minute gradient. So that's the kind of sample set we would set up to first start tuning fragmentation. No deuterated water near the stuff. Well, think about it. Let's say you've got a protein that's only at 1 milligram per mil. We can cheat. We'll say, well, we're just going to dilute it in something up to 20 microliters. You can cheat and say, well, we don't have very much of the protein. It's very dilute. Well, let's just not dilute it in as much buffer to get it up to 2. We'll add 10 microliters of the stuff, plus 10 microliters of water, regular water. In a functional deuteration experiment, that would be deuterated water. So when an investigator comes and we're first starting to tune the fragmentation, we can use a less concentrated sample to do that. You understand what I'm saying? But they know they need to get the stuff more concentrated a week from then, whatever, another sample of it, another batch, for doing the functional deuteration. Okay, does that make sense what I'm saying? So, and very commonly people show up and they've got stuff fairly dilute. Oh, well, give us a week, we can make it more concentrated, make another batch. But we can start right away with the other stuff. Then what we do is the output of that data of those, so what do we call that? So fragmentation tuning is what we would call that kind of experiment. If you saw no fragmentation at all, the first thing we do is run through something we know should fragment to make sure that hasn't been a failure of the pepsin column or something. These solid-state columns are extraordinarily robust, but you can kill them. And we've never done it on purpose, but we've definitely killed them. And probably it's because accidentally letting a neutral pH buffer flow through the pepsin column. Nothing hurts pepsin. Guanine thiocyanate, guanine hydrochloride, as much as you want. Wash it away, it's all set to go. Makes them meaner, like prion proteins. Denaturing this pepsin in solid state, it's all the different solid state, makes it great. But just the tiniest time at a pH of 7, it's dead forever. pH 6.5. So accidentally letting the wrong slug of buffer go through there is dead as a doornail. Just got to scrape it out and do something else. Your protein, do you have any disulfides in there that you know of, either the PRP or the transthyretin? Okay, something to keep in mind, do they contain any cysteines? Okay, we've had the experience very commonly of people, there's artifactual disulfides. After your during preparation, whatever, you've got some folding and it causes trouble. Your protein, you know it has lots of disulfides. That's at the center of the whole game there. So we've worked out methods of reducing these. The basic problem in reducing them is that most reduction that you use in biochemistry with proteins involves disulfide exchange, turmeric, ethanol, DTT, whatever. And that requires a neutral pH for it to proceed. Below a pH of 6, those things just don't happen, certainly in the cold. So we use acid-reactive phosphines that will work just fine under these acid conditions. It's tricky, actually, because where they fall off the cliff in terms of activity is right at pH 3. The literature will say pH 2, but that's as measured in temperature. We're doing this in the cold. So it's a bit of an art to using the phosphines, but basically we use very concentrated solutions of them. And we've found lots of times that people who have no disulfides in their intracellular protein, they get a crappy map until we throw the phosphines in there, and bam, all of a sudden there it is, nice. That's exactly what the problem was. So I would suggest we won't use them, but if you have any trouble, we'll do a few whacks with that just to make sure. So when we do use the phosphine-containing solutions, typically that will be added at the moment of quench. So the quench solution will have guanine hydrochloride in it and the phosphine, usually at about 1 molar. That's mixed, and depending how mean the disulfides are, it'll either be no purposeful pre-incubation or incubated for 5 minutes. Those are the experiments where we pre-incubate for 5 minutes and then process. And if it's going to be a frozen operation, you'll incubate it on ice for 5 minutes and then freeze it to -80. It's all set to go. You probably won't need to do that. You'll definitely be doing that. And we just make up a big batch of that solution and use it until it disappears and make another one. And how well it works, varies from batch to batch. Some very precise pH differences appear to make a difference. Okay, so what happens is, so during the fragmentation tuning step we just talked about, we've talked about we will empirically just start with a range of denaturant concentrations, a couple of digestion times, and you could just arbitrarily choose one of those if you wish. And again, if you have limited time to do it, if you just want to see if it works, you can always, we would probably guess, choose 1 molar guanylate chloride for 2.5-minute flow rate. That gives okay fragmentation with most proteins, just picking that one. But tuning it, you're going to increase by probably a factor of 5 the number of fractions you get. So something simple like that for a survey. How do you tell what you're getting? Well, the effluent from this is being sprayed, so this 50 when we dilute the gradients, it's going about 50 microliters a minute. It's being sprayed into the mass spectrometer. For the fragmentation tuning, we use our LCQ ion trap mass spectrometer. The great virtue of that particular machine is that it's very good at doing data-dependent MS2. The approach we take is that as each peptide comes out, the mass spectrometer first of all says, tell me everything that's here on the whole M to Z axis, and it measures everything that's there. Then we instruct it to take the most prevalent peptide at that instant. If you're familiar with the idea of scans in mass spec, repeated acquisitions over time of a stream of stuff that's coming in. Typical scan operation, you think of a scan as occurring once every second, the way we run things. In fact, there's lots of scans that get averaged, but thinking about every second. So an MS1 scan is done. MS1 meaning you tell the mass spectrometer, tell us everything that's in a spectrum between 0 mass and 2,000 M to Z's, what's there. And typically we'll say in the very next one, pick out the most prevalent one in the previous scan, MS1 scan, and do MS2 on them. So what it does, it isolates that peptide in the ion trap in the second scan and cracks it by giving it extra energy. And then it spins that out of the trap and measures the size of all the fragments. And then proceeds with whatever else we tell it. What we do with that data, so that's called MS2 data. And what we do with that data is when we're all done, we pump that into a program where it knows the size of the fragment before it got cracked. It then knows the size of some of the fragments after cracking, not all of them. Many of the fragments are small, buried in the noise, whatever, but it knows the size of some of the fragments. And then you allow it to search in a library of possible sequences what fits that. If you have this like this and this, and the trick to this is that the fragmentations always occur in the polypeptide backbone. That's the trick. So with that simplifying assumption, you look to see in this library of sequences what are your possible peptides. And what we do is we just give it one sequence, transthyretin or PRP or acetylcholinesterase. That's all it gets. So you think a pretty simple exercise. Well, it turns out still there's lots of possibilities. The way the software works, it'll always make a guess. It is committed, it must make a guess. And it gives you a little bit of an idea of how good of a guess it thinks it's made. It'll attach a number to the guess. We call that the X-core number, X correlation or something. If it's a really good number, it's pretty sure. The way it does this is it runs through your library of sequence and it makes a first guess. Then it backs up to initial conditions and run-throughs and does it again. And if it comes up with the same guy most of the time, it thinks it's it. If it comes up with just sort of random different guys, but it has to say it's one of them, the most common one, then it's less reliable for a variety of reasons. So it takes a guess as to what it is. So what we have is for every peptide that the mass spectrometer was able to do MS2 on, we have a proposed identification from the sequence. That's the output of that data analysis. Now let's think about what's really going on. Remember, during the LC, I said between 2 and 10 peptides could be coming out in any instant, right? And the width of each of those peaks is 20 to 30 seconds. So you better be very fast at doing this. If it takes a second per scan to do an MS2, then it's no good to identify, let's say, half the peptides that are coming out. By the time you've done that, they've stopped coming out. The other half has stopped coming out. You've passed them. So we do what's called data-dependent dynamic exclusion MS2. Data-dependent means that in real time, it's going by what's happened immediately before to determine what it's going to do now. Dynamic exclusion means basically what it's doing based on information. So it does an MS1. One of the common modes we use, again, these are evolving too, because there are optimal ways and less than optimal. We've empirically tuned this, but basically, at present, we have basically, during this data-dependent MS2, a regime something like this. It'll do an MS1 scan. It takes about a second. And it basically displays everything that's coming out at that instant in the chromatography. We then say do MS2 on the first most prevalent ion that you saw there. It does that. Then the next scan after that is do MS2 on the second most prevalent that you saw in that first one, MS1. And then the next one is third most prevalent. And then you tell it to do another MS1 scan. So basically, it's 4 seconds. So the MS1, then MS2, 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 4 seconds to do MS2 on 3 peptides. And then what we tell the machine is ignore those 3 peptides for the next 30 seconds. Even if you see them again, we don't want you to do MS2 on them. The problem is that the concentrations of peptides are changing all the time. They're going up like this. And you can imagine it being very complicated choosing exactly where you do the MS2. Here's the bottom line. We have found, at least for now, even the chromatography we're doing MS1, then MS2, 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 then repeating it, excluding those other guys from being looked at again for a period of time, is the best way to do it. You don't want to exclude those masses for too long because who knows, 30 seconds down the road another peptide comes out. It's a different sequence, different peptide, but it's got exactly the same mass as the one you already said don't spend any more time on. That happens all the time, very commonly. It accounts for 20% of the peptides that you lose by not doing this. So we program these in. We do this already. But you're going to see the output come out. You'll see this big possible list of peptides. And so in a typical fragmentation run, one run, there'll be 1,000 possible peptides, 200 to 1,000 possible peptides that it thinks it's identified. Probably vast majority of those are incorrect identifications. What we then do is run that, so you've acquired, let's say, 20 samples that way. So you got all this massive stuff. We now take it to this software that Chris actually knows how to work pretty well now, but he's not the world's expert on it, where we use that software to filter through that stuff to see which ones are correct guesses. And also to judge whether it's going to be useful to use the probe. So what you want is you want to identify the correct peptide, right? You want to know for sure that it's really the sequence you think it is. You want to know where it sits in the whole, sequence of your protein. There's got to be enough of it there so you're going to be able to follow it as you deuterate it. Okay, we'll discuss later on the various things that figure into that, and so on. And so we use the software in one mode to help filter through those things. One of the ways we do it is the main functionality the software was written for was if you already knew what the peptides were, let's say God whispers to you, or you spend 2 months figuring out what all these peptides are through some method. Then if you have a list of peptides and when they come off in the chromatography, to put that into this software and have it filter through LCMS of deuterated fragments, find the right peptides, capture them, tell you how much deuterium is on the thing, and then go on to the next peptide. That's what we designed it for. The trick we use here was to acquire just MS1 data in parallel with this data-dependent MS2. And what we then do is basically take that program, we say this is the list of peptides that we want to find, and we tell it to find it in the undeuterited data that we acquired. We already know what the shapes of all those curves should look like with all these isotopic envelopes of all these undeuterited ones. You can just calculate what that is. The extent to which the software guesses correctly on those is our first level filter. This will all become clear to you as you go through the software. But basically what we do is we, in a sense, use the software in reverse that we made to function as a very powerful filter to throw away most of the peptides that were wrong guesses for a variety of reasons. You don't necessarily know what they are. There's other strategies we can do to figure this out. Once you're done with this, you have a peptide lookup list. What do we call it now, Chris? What is that called? Is it called a peptide pool?
Yeah.
So you have a set of peptides, the peptide pool, which are things that span, if you're lucky, they span the whole sequence, they're multiply overlapping, and these are peptides you know you're going to be able to follow. That peptide pool will then be used against any fragmentation data you get from deuterated samples. And you just run that peptide pool against all your various samples. And you make these pools in various ways. It may turn out, let's say you've discovered that of your whole protein, the ones down at the N-terminus, beautiful fragmentation patterns in 50 millimolar guanine chloride. But all the rest of the thing, it needs 4 molar to get the beautiful digest there. Then you could double acquire the samples. You can prepare samples in both ways, acquire them both. Very often we'll take the peptide pools that work against these peptides and the ones here and combine them into a super pool. So you don't have to keep changing the peptide pools you're doing all the time. You simply are changing the yield. The software runs either taking the peptide pools either to name peptides, determine you've identified them correctly, or to, once you're sure that's right, calculate how much deuterium is on them. The software runs and does that. When it's doing that, I don't know, it depends on, we keep getting faster and faster machines, but typically when you set it up to run like that, it'll run for 20 minutes, an hour, 2 hours on its own. Then it's done. It makes errors, either in identifying things correctly or in correctly setting things up for calculating how much deuteration, somewhere between 3 and 15% of the time. The rest of the time it's done it exactly right. The problem is you don't know which are right and which are wrong. We've set up a couple additional filters that you now use to screen those out. So this is in fact what you end up spending a major amount of your time on. It's already done 9/10 of the work, or 98% of the work, but you have to go through and figure out what it did wrong. And that's the first step. You figure out where it made errors and throw them away. Or if it's made an error that you can see is fixable, you basically fix it right there. And we teach you how to do that. And the software is designed to facilitate doing that, the editing function, proofing function. And basically what it boils down to is you just flip like this through each guess that it did, okay? And each time it does that, in blue, it'll have displayed a tracing of, if it did things correctly, this is what it should look like. And in red is the actual data that it's got displayed and processed. And you look at them, if they totally overlap and they look perfectly fit, obviously it's right, and you're just off to the next one. If they're different, then you know it was off in some way. And you look to see if the difference is something you can fix. If it is, then you go to fix it, whatever. But that's what the majority of your data reduction time is doing, is flipping through proofing those. Dennis has developed another approach to doing this. Let's say you've got a time buildup curve. You're on exchanging some protein. So any peptide in there can do nothing but increase the amount of deuterium it's getting. And it should be a smooth function of time. You don't know what it is, but it should be a smooth function. So his screen, he said, you know, he's lazy, so he doesn't want to do this. So he says, well, I don't want to proof schmoof. I'm not going to sit there forever. I'm going to have software just accept everything it's got, but plot it all out. And let's see which are smooth curves. And the ones that are nice smooth curves that build up the whole time, they're right. The ones that go like that, bam, back like that, something's wrong with that point. That's the point I'll look at and see to fix it. And it's a great help. So some combination of those two things, you can use the behavior for protein experiment as the filter also. Again, we'll get to go over these again, but you'll discover this is what you finally, if you get your dream and you get a great fragmentation pattern, and this is a useful technique for you, that's what you're going to be spending most of your time doing, is massaging those guys. So you want to learn all the tricks for quickly filtering through that stuff. Okay, we have two kinds of mass spectrometers here. One is this LCQ ion trap mass spectrometer. Beautiful for doing the data-dependent MS2. It's really very good at that. Its shortcomings, so it's very good for that fragmentation tuning step, where you very quickly want to know what you've gotten so you can try out another set of conditions, whatever. to identify the peptides. Its shortcomings are a direct function of why it's so good at doing the MS2, which is it has comparatively low accuracy. So it'll say something's a certain mass, and it could be that plus or minus a certain tolerance, which is a lot bigger than with other mass spectrometers. So there's also resolution. It'll say the peak is, the mass is that, it's subject to widths being this large. So if there's another mass that's slightly near that, it can be buried. We have another mass spectrometer in there called a QTOF, a time of flight mass spectrometer, whose data-dependent MS2 capabilities are clunky, and so we don't use them at all, but its MS1 capabilities are unparalleled. So there's extraordinarily high mass accuracy and resolution. So in general, what we do now is we do the fragmentation tuning on the LCQ. Then once you've got that down, you're going to do all your deuterated experiments on the QTOF machine. As I mentioned, we probably lost you in a little bit while back, how we do the fragmentation tuning really is to acquire data-dependent MS2 and a parallel MS1 acquisition. We make the software work those against each other. Only things that both agree are correct identifications are correct identifications. We have found that the best way to do that so far is when we're doing the chromatography on an undeuteurated sample, half the stream is shot into the LCQ and the other half is into the QTOF. So both mass spectrometers are occurring simultaneously on the same sample set, each one getting 25 microliters a minute. And that's how we've been doing things so far. It actually works pretty good. So that's that. Okay, and so I've been alluding to the software already several times. Let's see, mini introduction to mass, you going?
Mm-hmm.
Okay, so this is mini introduction to mass spec. So who here knows a little bit about mass spec? A little bit electrospray mass spec? LCMS mass spec? Okay, good. Okay, let's see. Most people that don't know much, most biologists, when they think about mass spec, they, where's the magnet? Most mass spectrometers don't have magnets anymore except for little sticky magnets on the outside. Right? Pull up your notes or something. They do all the separation and measurement of things through electrical fields, no magnetic fields. I'll give maybe about 10 minutes of an overview, and then I'll very much focus in on what the absolute bottom line of what you've got to know for this. The points I need to review for you to make sense of things is you've got to know what an M to Z axis is, what M to Z and what the implications of that, what those mean. You've got to know what an isotopic envelope is. You've got to know of the importance of varying charge state of your peptides. At least to start with. Okay. When you talk about different kinds of mass spectrometry, you can it's sort of like different kinds of cars, let's say. You could have a certain kind of car, but really it isn't a car unless it's got the tires on it also. And the tires you can have can vary depending on the type of car. The type of motor can vary depending on the type of shell. So basically you talk about different functionalities that different things can be glued onto. And they all have different virtues and stuff. Some of these fit together so well, some of the different steps of mass spectrometry fit together so well that we forget that you can mix them together in virtually all kinds of combinations. So the kind of mass spec that is conceptually easiest to think of and actually easiest to use is what's called MALDI mass spec, matrix assisted laser desorption ionization. Okay, MALDI. And what that is, that's basically, so let's think about the modules of mass spec. First of all, you have to make ions somehow. So there's the making ions part. Then there's the, sometimes you want to fragment the ions before you further fragment them or fragment them again within the mass spectrometer before you do subsequent analysis. And then finally, there's the basically the part of the thing that measures the M to Z, the mass, whatever. So let's back up for a second. So M to Z means mass to charge ratio. Remember I told you that in mass spectrometry, nothing exists if it isn't charged. And again, everything I'll ever deal with you in is positive ion mode. So everything, the ions all have positive charges, they're moving around, so they're going to move towards a negative. All right? So if you think about the forces exerted on a molecular species, whatever force it is, if it's a charge, if it's dependent on the charge, it's going to be a linear function of the charge. So if there's X amount of force, if it has a +1 charge, if somehow you get a +2 charge on that peptide, the amount of force is going to be twice as much that's exerted, and so on and so on. So that's why it scales directly with the amount of charge. You cut the mass in half, the force is going to be the same, but how it responds to the force is going to be different. So, in other words, accelerating, as you accelerate, if something's half the mass of another thing, it's going to accelerate at a very different rate than the larger thing. Okay? So that's why there is nothing about a mass spectrometer that'll help you directly tell what absolutely the mass is. Everything that happens in there is a direct function of the M to Z, mass to charge ratio. Now, is that pretty clear? You're comfortable with that? So typically, MALDI, in that the ionization, to make the ions, they basically start with a solid, your ion is in this solid material, a laser beam shines on it for a brief period of time, vaporizes some of the material, and along with that vaporizes some of the peptides you're trying to follow. Almost always in MALDI, you've already done the fragmentation of peptides before you put the stuff in there. We're talking about peptides. So you bounce, it's all in a vacuum. Everything's sealed in a vacuum. So you bounce up into this vacuum, this big cloud of ions, a tiny fraction of which is the stuff you're interested in. It's then, there's an accelerating voltage. So that's positive, negative. And so when all this cloud is generated, all the ones that are positive are going to start accelerating down to this guy, right? And they will accelerate. In fact, they don't accelerate the whole time. What you do is you have what is in essence a ion gun. Ion guns, as I understand it, the basic trick, if you have a positive and a negative here, and you all of a sudden put a positive here, it's going to come over to the negative, all right? But these are basically points if you arrange it right. So it doesn't really hit it, it's going to oscillate around the thing like that. Well, what you can do is if you put up a shield here, a Faraday cage, in other words, you basically, in effect, put this inside of a steel box with there just being a little hole here. What happens is, if you accelerate something, once it gets to here, it's going to go that far and then come back. But once it's gone through here, it can't see the field anymore. So it keeps going with constant speed. So an ion gun is able to accelerate things, and then once it passes this cage limit here, it doesn't experience the field anymore, except for the tiny little point that's right there, which is 0. So they'll go at constant speed. So you can accelerate things over a distance and then just have them fly. Okay? In the MALDI, the ions will be generated, little cloud, they then start accelerating over a certain part of that distance, and then they're allowed to just float. If they're different M to Z's, different species, they're all going to get going at different speeds. They're accelerating at different rates, so that when they finally get here, they're all going at slightly different speeds. And then you just let them float across here at those fixed speeds in this vacuum. The flight chamber. Right? So time of flight, TOF, time of flight, is how long it takes to get from here to here, when everybody gets a fixed accelerating force. So ionization by a laser here, then the flight chamber, and they'll have a detector where basically just records splats against the wall. So things hit the wall here, variety of detectors that just record this shower of splats, that it can pick these up very quickly and record the time. You calibrate those with various things. You can calculate what the M to Z is. You don't know what a particular M is and Z is, but you know what that ratio number is. Okay? Some of the tricks, this laser desorption, so we're just talking peptides now, proteins or peptides. Not talking any other kind of species, so it's a big simplification. A lot of the stuff you'll read is because they're talking about some other kind of biomolecule. But in general, with laser desorption like this, the peptides will pick up 1 plus 1 charge state, and that's it. So in MALDI stuff, in fact, everything is plus 1. You never think about it anything more than that. It's all plus 1. Okay, the more fancy machine in there, I told you we had the QTOF, right? What it uses is electrospray to generate the ions, and I went through that very briefly. But basically, what happens is you have your liquid is coming down here, your chromatographic liquid is coming down here, this little tiny needle, and it squirts out the end. This is charged up to, and then here's the mass spectrometer body per se, with this little hole in it. Okay? So this stuff is squirting out of here, and around it you have this torrent, this hurricane of hot helium gas, nitrogen gas coming along here that helps to atomize this. What actually happens is, this is all well worked out. When you look at this little tip here of juice coming out, what happens is you charge these drops. So imagine these are drops coming out. They get charged, a certain number of positive charges, and as this stuff evaporates, the charge density starts building up on that drop. The charges don't magically disappear. Most of the solute, most of the solvent that's here is neutral, right? Water, acetonitrile, as they evaporate, they don't carry away charges, right? It's all, the charges accumulate here. So the charge density on this drop gets bigger and bigger. A whole bunch of positive charges don't like each other. They tend to like to go on the surface, right? It'll get down, what happens is it gets, the drop will get down to a certain small size and basically explode. It just pops. And when it pops, in a very short time period, the remaining solvent is removed, and all the little things that can still retain charge do retain some charge. So that's the instant of ionization. This is called a Taylor cone, this little thing where all these little drops are popping and everything. So what probably happens is that during that spray, if you've arranged it vaguely right, even though the nitrogen gas is at 200 degrees centigrade, the drops are still at 0. They're evaporative cooling. It's keeping them cold until that pop. And now there's no water in contact with the peptide, except for water vapor. And so it's inefficient. If you think about it, this temperature coefficient I told you about, in terms of every factor of 10 for every 20 degrees, this is at 200 degrees centigrade, right? So that's got to be going a million times faster. Billion, I don't know what, it's some really amazing times faster. So even a few nanoseconds, if it really were there, it'd flash off all the deuterium that were there. It doesn't happen. There's really very little loss in here. You have to go above like 230, 240 degrees before you start finding any drop-off in terms of temperature here. So you're spraying these guys. Here's the trick to electrospray. Electrospray produces a range of charges on the particles, okay, on those peptides. It can be +1, +2, +3. And here's the rule. As probably in solution, when they're in the liquid there, a peptide is going to have probably a number of charges you'd guess by simple, what you know about peptides. Let's say you've got an amino acid at pH 2, a peptide at pH 2. The carboxyl end is going to be protonated, so it's not going to be charged. Side chains, if they've got amino group or guanidino group, are going to be charged, and the N terminus is going to be charged. You can actually add up how many charges it's going to be. So that's true in liquid phase. But the minute they're volatilized and they're generated as these little guys, the charges can move around. They don't have to stay there. And extra charges can go on. So it is not, you can have a peptide that, it's got amino terminus where you can pick up +1 and nothing else, and you can find a +2, +3 charge state of that. They're mysteriously moving around somewhere. It's got something to do with this ability of these hydrogens to migrate too. So the bottom line is that depending on the sequence, there'll be a propensity towards having a certain charge state, but it can vary a lot beyond that. It's not going to be below +1. It's going to be integer value. And so things that are rich in arginines, lysines, are going to tend to want to have, what you see is a way mass spec software likes to represent things. The stuff is really built to very quickly change scales and normalize itself to facilitate your interpreting the data. So without you even knowing it, very often when you have a screen display something, it'll normalize so that full vertical scale will be the most prevalent thing there. Whatever it is, it makes that 100%. So everything else is relative to that by definition. Okay? Got that? You're dozing off on me there. Okay, you sure? Okay. All right. So typically, let's say one species. You'll get something here, let's say at 1,000. And let's say that's the +1 charge state. The +2 charge state, that'll be at 500. Okay? And let's say these are equal quantity. The +3 charge state will be what? I'm guessing, what would that be? +3, 250? I don't know. Something. Anyways, there'll be relative numbers. Okay? So you'll have one that's predominant, this and this. In electrospray, with the kind of peptides of the size we're talking about, probably 2 of the charge states account for 80% of the material under any condition you're spraying and doing stuff. You can tune the ratios of those a little bit by how you're running the machine, the voltage, the concentration, other stuff, but it's pretty much built into the peptide, really, what its predominant one wants to be. Okay? So that's the range of charge states you can get. So first thing, mass spec software loves to normalize things to what? Well, the biggest thing that's there. You can override that with keystrokes on there and on the thing. You can override that. But in general, when you first look at things, realize it's chosen one of these things to make it full scale. So you better, and you almost always here it'll say what its normalization factor was. You got to get used to looking at this, because you'll look at 2 sets of data and you say, boy, those look the same. You didn't bother to look here and see that, oh, there was only 1,000th the amount of stuff in that second run as the first one. Because it's so good at normalizing, you forget. You only pick it up sometimes where you see the background appears bigger in one than the other, unless you know to look. And this is where that problem can come up, where you've acquired a whole bunch of runs. Hey, they look pretty good at this level, but that's because it's normalizing everything. If you back up, you find that one, it missed everything. Run didn't even run. It's 1/10 or 1/20th the amount of material, which is what we get carryover between runs. Okay? So it normalizes. Secondly, this is, in general, the horizontal thing is going to be this M to Z axis, where it starts off somewhere near 0. We tend to not spend much time with things that are below 200, because we're interested in, remember, I said that the first amide, the N-terminal amide, we can't follow very well. It exchanges really fast under quench conditions. So there's one amino acid, there's this one that goes really fast. So really a tripeptide is the smallest thing we have any use for in this game we play. Because a dipeptide has got one that's just going to exchange so fast we won't see anything. Tripeptide, average amino acid is what size? 125, 150, when I think about it. So 150, 150, 150, 450. We don't have much business looking at things much below 450. So this lower limit, though you can think of it as 0, is often like 200 or 300. We avoid spending time on chemical adducts of acetonitrile, other kinds of stuff. So down here, and this one up here is around 2,000, okay, something like that. So what happens is, I've told you the general rule that your peptide, remember we're talking about things that are, 10 to 15 amino acids here. In general, they're going to have, some +1, some +2, some +3 in this range. There's a little trick, and that is that if you just watch to see what happens to peptides, every time amino acid sequence gets above about 1,500 Daltons, it'll add another plus charge, on average. Okay? So every 1,500 Daltons, it'll add another plus charge. So that's why on this axis of 0 to 2000, which we very commonly display, you'll see whole proteins. So if you charge up a whole protein, okay, let's say, it's recording. It was warning you it was going to be out of tape, I think.
Oh, okay.